Um, Thanks, everyone. Welcome to my talk on Kubernetes at Datadog Scale. My name is Pulido. I'm a staff developer advocate at Datadog. And if I turn this on, yes. This talk is not about Datadog itself. It's how we run Kubernetes internally. But just so you know who we are, Datadog is a monitoring and security platform that is going to help companies improve the observability and security of their infra and applications, including, of course, Kubernetes as a platform, but also the applications we run on top. And being this a DevOps conference, probably all of you know already this, just in case, Kubernetes is a container orchestration platform that is going to help you run your containerized applications in production. It has nice features like auto-healing, auto-scaling. It's completely open source. It was built originally by Google based on the ideas that they had with their internal orchestration platform called Borg. So based on those ideas, they started from scratch. They created this project called Kubernetes, and they released it as open source. They donated it to the CNCI Foundation, and it's been a huge success since then. So as an open source project, it's amazing what they have achieved. It's 25 major releases in 2015, more than 100,000 commits coming from 3,000 contributors, more than. So definitely a super, super successful project, probably only behind Linux itself, and hopefully it will stay like this for a while. So as an open source project, it's clear that it has been successful, but what about its popularity? So this is not your electricity bill on the past year, although it could be. But this is Google Trends for Kubernetes searches. And Google Trend is relative numbers. It's not an absolute number. It's more or less like the first derivative. So this is from the beginning, from 2017 to end of 2021. And when I saw this graph, there are a couple of things for me that were very, very interesting to analyze on this graph. And the first thing is this. I think the Kubernetes has reached a level of maturity. It has, in a sense, what we call has crossed the chasm. At the beginning, there was hyper growth, exponential growth on people building hype around Kubernetes, very much needed when you're starting an open source project this big. You need a lot of people talking about it. You need a lot of people going to conference. You need a lot of that to make it grow. But once it reaches the enterprise, once it reaches really critical workloads, you need to slow down. And it continues growing, but it's more a linear growth rather than an exponential one. And the second thing that I found on this one, and by the way, the maturity also, and this slowdown on growth, and it also, for example, they changed the release cadence for every 3 months to 4 months, for example. The other thing that I found on this graph interesting is that there are some outliers on that graph. It feels like it's growing, and then it drops and grows again. And one of the things that we love doing at Datadog is putting different type of metrics, different type of telemetry on the same graph to try to find correlations. And we all know correlation doesn't mean causation, but in many cases, finding good correlations may help us humans try to understand and try to find the root cause. So when I saw this graph, I had an hypothesis. And to try to find if that hypothesis was correct, I decided to graph on the same place Google Trends for Mariah Carey's classic, All I Want for Christmas. And when I did, this is what happened. You can see this fantastic, perfect correlation. Obviously, the root cause is that it's a holiday season. People tend to take time off work, and therefore search less for work-related stuff. If correlation meant causation, it would mean that once a year, we don't know why, a bunch of people drop everything they have to do with Kubernetes to listen to Mariah instead. It could also happen. I do that, so might be more people like me. Cool. So if you want to see other insights on container usage, Sorry, not related to Mariah or any other pop culture, but if you've, Datadog releases once a year their container report, which is based on the data that we get from our customers. We release a report on how people are using containers, how people are using Kubernetes. The latest one was released just a couple of days ago, so the 2022 is just out of the oven, so feel free to have a look. But I've come here to talk a little bit how we run Kubernetes internally. And Datadog has been around for 12 years, more or less. Kubernetes only for about 7. So obviously, if you do the math, we haven't been running Kubernetes forever. We cannot say that you need 12 years of experience of Kubernetes, like some people do, because we know it's impossible. And so for us, Kubernetes was a migration, like many people. And the reason why, when we were deciding to move to containers and orchestration, there are several reasons why we chose Kubernetes. If you put it on the eyes of 2022, now it's like a little bit like the de facto choice. Back then wasn't the de facto choice, but we decided to choose Kubernetes for some reasons. The first one is that we loved the model of Kubernetes. Everything in Kubernetes is API-driven, it's completely API-centric. This is actually one of my favorite features in Kubernetes, and I'll be talking about it a couple of times during the talk. Second reason, the large community. Those 3,000 contributors don't come from anywhere. It's like a lot of companies have a big stake on making Kubernetes successful. They are putting a lot of money, a lot of engineering effort on making that happen. So that's also very good when you're selecting an open source project. Another reason, we run on multiple clouds. So even though you still need to use the cloud-specific APIs, we run on public clouds. If you put a layer of abstraction in terms of compute that is common to each of those, at least some of it is going to be common. And the final reason was mostly business-specific. We wanted to make Datadog the best platform to monitor Kubernetes, and the best way to do that is running it ourselves, because we run very big clusters, and we monitor our clusters using Datadog as well. So if we are able to do it, our customers will be able to do it. So what scale are we talking about? So we have dozens of clusters, some of them with more than 1,000 nodes. As I said, we run on multiple clouds. We run our own control plane, so we don't use managed Kubernetes on those clouds, because we need to be able to control a little bit more specific everything on the control plane as well. It's not like the normal choice, but it's our choice anyway. And for the rest of the talk, I'm going to be talking about some of the decisions that we made along the way. Some of them were very, very early on. Some of them are being through the years. And kind of a spoiler of what I'm talking about is, in a way, when you start using Kubernetes, Kubernetes becomes a platform to build platforms. And a lot of the things that you need to do is to think about, for example, what interfaces are you going to expose to your users, what interfaces you're not going to expose to your users. But I'm going to be talking about 3 things that we did. It's not everything that we do, but I had to choose something for the talk. The first thing is networking, and specifically pod networking. So pod networking, so a pod in Kubernetes is the minimal deployable unit. It's basically one or more containers that are going to share the same networking namespace. So any container inside the same pod is able to talk to each other through localhost. And pod networking is basically the rules that tell you how pods talk to each other. And it's basically these 2 rules. Every pod in the cluster is going to get a unique IP. And every pod can potentially talk to any other pod in the cluster. So obviously, then you can do something like network policies to avoid that from happening. But the traffic is routable. You have routable traffic between any other pod. The tricky thing here in Kubernetes is that this is not implemented by Kubernetes itself. It's implemented through plugins that implement the container network interface. The container network interface, also part of the CNCF Foundation, it's a spec that defines, if you want to write one of these networking plugins that implement pod networking and other things, how you should write those plugins, and also how they can interact to each other, because you actually can mix and match. You don't have to use a plugin for everything. You can use one for network policies, one for pod networking, etc. The thing here is that there are many, many different implementations of CNI plugins, and they work very differently. So even though they all follow the same spec, internally, they all work very, very differently. So probably the first thing that you need to choose is to decide what CNI plugin you're going to use. If you're using managed Kubernetes, probably that choice is made for you, although many of the clouds for their managed Kubernetes offering, they offer several options. So even though you're using managed Kubernetes, you can choose between maybe 2 and 3 one of those plugins, but you need to understand how they work. When Kubernetes started, the most common one was network overlays, and this was very simple to start. It was easy to debug, easy to understand, but the problem as people started growing Kubernetes and having more and more nodes, if you use something like network overlays, adding the IP on IP every time that you have to change nodes can be a little bit of a bottleneck. So in our case, we decided to choose direct port routing. Direct port routing, basically, if you're running on a public cloud, you're able to leverage the network of your cloud, the software-defined network, and basically assign an IP of the VPC that the cluster is running on, instead of doing any NAT or any overlay. This is not only one thing that we choose, but it's also, for example, the default if you're using EKS on AWS. They use direct port routing. It's an option on AKS. It's not the default, but it's an option. So if you're on Azure, you can also select the plugin that does direct port routing. It's also the default one for newer GKE cluster, not for every cluster, but for newer ones through IP aliases. So this is very good because you don't have to do the IP on IP. You don't have to do any NAT. And you can also route traffic not only between pods, which is the goal of pod routing, but also between any other compute, like any serverless function or of VM that you have running on the same VPC. So this is what we do. But the thing is that we run on multiple clouds, and these plugins are very, very cloud-specific because they need to understand how to create a network interface in the cloud through the right API, in the case of, for example, creating an ENI, something like that. So the thing is that we had, for many, many years, we had to maintain 3 different plugins for all the clouds, depending on the cloud that we were, until we came up with this project, Cilium, also part of the CNCF. They started on 2019, more or less. That's at least when we started talking to them. We approached them because they implemented host-to-host encryption, and we wanted to use Cilium for that, only for that at the beginning. But it ended up being like a networking solution. So Cilium is a networking solution for Kubernetes based on eBPF. And if we fast forward these 3 years, we've been working with them. Right now, it's the CNI plugin that we use for our clouds because they do direct port routing, but for multiple clouds. So instead of having to maintain different plugins, we can only use one, which is great. We use it for network policies as well. We use it as well for service networking. So one of the things Cilium does is that it replaces kubeproxy. So if you don't want to use IPVS or IP tables, like the default kubeproxy, you can use Cilium as well. And of course, the reason why we went with Cilium, which is host-to-host encryption. Good. That doesn't mean that everything worked for us out of the box. We've been we are some people in the Datadog team are maintainers of Cilium. We've contributed to a lot of patches. So, and if you're interested about more details about how we do networking, many people on the compute team in Datadog have been giving talks at KubeCon about networking in Kubernetes. So that's a list, the things of KubeCon talks that are very, very specific. Many of them by one of our engineers, Laurent Bernet, who is fantastic and knows a lot about container networking. This is a gist, by the way, in my GitHub profile, so if you don't catch that URL, you can try to find it that way. Good. So the second thing I wanted to talk about is developer experience. And again, when you're building this platform on top of Kubernetes, you need to decide things that you're going to expose to your users, things that you're going to hide to your users. And one of the things that we decided is that we wanted our users to know that they're using Kubernetes. Obviously, they don't have to know everything about Kubernetes, our developers, but they understand where they are. They need to understand what a deployment is. They understand how a rolling update works, for example. And one of the things that we decided to do in terms of developer experience is as much as we can to use the Kubernetes resource model. So we believe that one of the great successes of Kubernetes is this, the Kubernetes resource model, and it's a great developer experience. So instead of trying to build something completely different on top, reuse what Kubernetes is already good at. So what is Kubernetes resource model? So it's basically how Kubernetes defines any resource in the cluster and the API machinery behind it. So how you create HTTP requests to the API. So basically, the resource model means that every object in Kubernetes is going to be very, very similar. It's going to have an API version. It's going to have the type of resource, some metadata, and then a spec that you need to follow. And once you have this model, you also have this declarative reconciliation loop in Kubernetes, which I think it's fantastic, in which instead of moving from imperative model on telling the cluster what to do, but instead telling it what it's supposed to look like. And then there are software called controllers that basically watch for that desired state and the actual state of the cluster and try to adjust it to be equal. So basically, the way you work with Kubernetes is you make this HTTP request to the API server by defining one of these objects. And then there is the controller manager, which is one of the components of the control plane in Kubernetes, that is all the time watching for new resources to be updated, created, deleted, etc. And based on that information, trying to make the cluster look like what it's supposed to say on the API server. And the great thing about Kubernetes is that this is super easy to extend through custom resource definition. So you can create new objects in Kubernetes very easily. I put an example of a project called Server Manager to basically request TLS certificates. And the way they work is following this Kubernetes resource model. When you create a certificate, you don't go and type, I want to create a certificate. You just define what that certificate should look like, and then you have a controller watching for those new objects, and all the logic is happening on those specific controllers. So for new extensions to the API, the model is exactly the same. So you make that request to the API server through these new objects, and then you implement a specific custom controller doing exactly the same thing. So doing this reconciliation loop of watching all the time for objects changing on the API server and do something about it. And that do something about it is obviously the logic that you have to implement. I'm not the only one thinking that this is a great idea. There are people out there saying that Kubernetes resource model and the underlying API machinery will enable a new generation of automation tools. We're going from an era of shell scripting to API-driven control planes. Less system administration, a more cloud provider. This is a little bit too optimistic, but at least it gives the idea of what we aim to do. Good. So another thing about developer experience, in terms of provisioning nodes in the cluster and anything related to compute in the cluster, we aim to be as self-service as possible. And one of the reasons that we started doing this from early on is because before we were using Kubernetes, our developers were used to just provision as well their own VMs for the services, so we didn't want to change any of that. But instead of using directly the APIs of the provider, we implemented as well controllers, and we decided to use this Kubernetes resource model. So at Datadog, when you want to, as developer, provision a node group for your service, what you do is to create one of these objects, explaining what cloud you want to be in, the type of instance, and some other options. And then we have controllers that actually do the API calls. So this is completely owned by the developer, and once they have their node group, they're able to send their workloads to that specific node group through, for example, node selector or node affinity and things like that. This, another thing is that those node groups are automatically part of a cluster of a node autoscaling group. So if those developers that suddenly run out of CPU or memory on one of those node groups, and they have a pod pending, this is automatically using the upstream, nothing fancy, Kubernetes cluster autoscaler that is connected to a cloud provider autoscaling group, and is going to provision for them automatically a new node for that pod that is pending. So this is how we started with Kubernetes, and this is how we run for many years. And obviously, this is not very Kubernetes native in the sense that every service had its own node group. So from there, we're starting asking our developer teams, OK, if your team owns X number of services, instead of creating one node group for each of the services, please reuse the node group for many of your services, and also try to request the right size of CPU and memory on your requests. The way we help them, and this is actually fairly new, we started implementing vertical pod autoscaler. Again, vertical pod autoscaler is part of the Kubernetes project. And basically what the VPA is doing is it will give you recommendations based on usage. So if you have a pod definition that says, I want 500 millicore of CPU, 500 megabytes of memory, after being running for a while, it will tell you, OK, actually, you get by with just 200 millicore and 50 megabytes. And the way the vertical pod autoscaler works upstream, and this is a very, very, very high-level diagram, so don't reuse it anywhere else, because it's missing a lot of things. But in general, what happens is that it has a component called recommender that is going to get the CPU and memory usage from the metric server. And then it has another one called the updater that can update the specification of that pod. But most metric server is OK to start, but we have a lot more data in Datadog itself. So what we've been working lately is to replace the recommender portion of the VPA with a custom recommender that basically, instead of getting the data from the metric server in Kubernetes, it gets it from the Datadog API directly. This is still very much in progress. We have a POC going on, and the goal is we are working on sending all those patches upstream as well. Good. So the next thing, now that we have a little bit more of beam packing, and hopefully teams are sizing their pods a little bit better, we are able to also enable an option in the cluster autoscaler in Kubernetes, which is repacking, which tries to reduce the number of nodes, obviously with the goal of cost saving. So with the repacking, you can basically, the cluster autoscaler is going to find opportunities to reschedule pods and trying to remove nodes, trying to really pack everything on the minimal number of nodes possible. And finally, the final step on this journey to a more Kubernetes native company, and again, this has been a journey of 6-7 years, so it takes a while. It's to really become a little bit more Kubernetes native in the sense that instead of developers having node groups that they manage, we offer what we call nodeless, which is kind of same thing as serverless, which they are servers, but nodeless, they are nodes. But those nodes are managed by the compute team directly, and they can be shared by several teams. If you obviously start from scratch a company today, and you decide to use Kubernetes from the early on, probably this is what you should be doing from the beginning and not after a big journey. And the third thing and final thing I want to talk about is policy enforcement. And again, we decided to expose as much Kubernetes as possible to our developers, but they are not experts. They shouldn't be. So putting some guardrails to make sure that things are, they know what they're doing, or at least if they don't, they get a stop. So for policy enforcement, we use Gatekeeper. Gatekeeper is part of the Open Policy Agent project. And the way Gatekeeper works to enforce this policy is through the API request. So when you create an API request against the API server in Kubernetes, it goes through several phases. The first one is authentication. Is this request authenticated or not? Then it goes through auth. And auth in Kubernetes is basically RBAC. So RBAC tries to answer questions like, can I do this particular verb, like create, update, watch, list, etc.? Can I do that against this type of resource, a pod, a replica set, a deployment, etc., on this particular namespace? This is more or less what RBAC in Kubernetes is able to answer. But once it goes through RBAC, it goes through a third phase called admission controllers. And admission controllers are able to further validate or even mutate a request. And all of the admission controllers are embedded on the API server binary. And you can actually enable and disable, if you manage your own control plane, enable and disable which ones you want to enable. But there are two that are very specific, and then they're usually enabled on any Kubernetes distribution that you may use, which are validated admission webhook and mutated admission webhook, that basically allows you to hook any external code to the admission controllers. And this is where Gatekeeper basically implements one of these, or in this case, two of these hooks, one for validating, one for mutation. And this is how basically it stops the HTTP request if it doesn't follow policy. And Gatekeeper, again, is part of, is completely open source, part of the CNCF as well. So really, really good project if you want to start implementing policy. What type of policy rules you can write using OPA? Things like have all containers specified a set of resource requests and limits, if that's part of your policy, of have the pod spec the needed security context. Are all containers non-privileged containers? If Linux capabilities were requested, are they part of the allowed list that we have internally? All these rules are not able, you cannot do with just RBAC, you need something more. And using something like Gatekeeper can help you. There are other solutions out there. It's not the only one, but yeah, it's the one we use. Gatekeeper, we like it a lot, again, because we try to, as much as we can, follow the Kubernetes resource model design pattern, and Gatekeeper follows this. So the way you create policies by creating an object, part of one of their CRDs, and there is a Gatekeeper controller that you deploy in your cluster that is going to watch for new of this object to be created, deleted, updated, etc. And another great thing about Gatekeeper, it makes a reuse of policy very, very easily, because the way it works, for every rule that you want to create, that you want to write, they use a declarative language called Rego. That's how you write your policy. But instead of having to write Rego code for each of the rules that you want to create, you create something called a constraint template, which is Rego code, but with parameters, and then you instantiate those parameters into as many constraints as possible. And we are not going to go very, very deep, or any deep, into how Rego works or internally, but just to give you an idea, this is how a constraint template would look like in Gatekeeper. So you have, again, following the same model, you have an API version, you have a kind, you have a name, and part of the spec, what you say is the parameters that that template is going to have. And you use those templates on the Rego code on the right-hand side of this code. It's part of the same object. I just split it into two because space. But basically, you have parameters. So if you want to do something like require labels for any type of object, you write the code just once, and then you can instantiate different rules, as many as you want, and have very different ones. Like in the left-hand side, it would be all namespaces in my cluster needs to have the label Gatekeeper. On the right-hand side, completely different rule. All pods on the default namespace need to have the do not delete. And because this is very common, reusing policy is very common that way, actually Gatekeeper has something called the Gatekeeper library. So if you go to GitHub, open policy agent, you will see all the repos there. One of the repos is Gatekeeper library, and people contribute to templates that you can reuse out of the box. And rules, specific rules, are going to be very specific to your use case, to your company, to your cluster, but many of the templates can be reused. So probably there are rules, for example, I don't know, images cannot come from external registries, for example. But then you instantiate that template specifying what registry is allowed. So if you want to start with Gatekeeper for policy enforcement, it's super, super easy using that library. And yeah, I'm coming to an end. So as I said, and the spoiler, Kubernetes can be the platform in which you build your platform. And low-level decisions like things like networking, whether to use managed Kubernetes or not, all that needs to be made by your compute team, your platform team, your SRE team, whatever you call it. One of the things that you will need to do is to think about that developer experience, how much you want to expose to your developers, how much you want to hide, how much you want to block. And no matter what you do, it's good to put some guardrails because as your organization scales, not everybody is going to understand Kubernetes internals, nor they have to be. Wouldn't be very productive to have a bunch of developers having to understand every single thing that happens under the hood. So putting some guardrails is also always a good idea. And that's it. Thank you very much. We're hiring. We're hiring, so if you think this is interesting, please come see me, or if you have further questions after a while. You may get a new job, I may get a new colleague, and a nice referral bonus. So that's all.
So I want a cut of that. Yeah, we have a lot of questions, so we'll try to summarize, and then there's Christian, so that the audience can ask, because I'll try to group them, right? There are a number of them around your organization internally. You described a little bit of this. Then some Kubernetes internal decisions, so let's try to group them a little bit. So let's start with the more or less organizational, let's say. So they're asking, like, how many people maintain the Kubernetes infrastructure? Wow. If you can share that, because sometimes, there's a bit of NDAs.
So it's a tricky question. First, I don't know the answer, so I would need to go to Workday, which is the application that we use, and start counting. But the thing is that it's not a low number; it's a big number. So and there are teams that do very different things. So we have a big team called the compute team in Datadog, and they basically do all the internals on the clusters. But then we have another developer experience, and they do all the things about how we build images, all the continuous delivery, all of that. And then we have the security team. And then, for example, Gatekeeper, in our case, it doesn't have to, but a Gatekeeper is maintained by people on the security compute team. So not a low number, quite a lot of people.
And in terms of like the rest of the technical organization, of course, Kubernetes has some complexity, well, significant, let's say. At the very beginning, at least, how did you get all the engineers to get up to speed? Did you had people in the team that were super proficient and then did internal workshops, or there was a time to train yourself a little bit? I guess this is for people who are trying to get deep dive into this.
Yes. But the question is more about
how did the team speed up in learning Kubernetes at the very beginning?
I guess like
everyone else, right?
Banging the head on the wall. It's the only way. Yeah. There were people like when Datadog started migrating to. I wasn't there back then, by the way. When they started migrating to Kubernetes, they also, before doing that, it wasn't like tomorrow we are going to migrate. It was a plan. And I know that they started hiring people that were already very good at certain things. So they hired specific people to drive that migration.
And people were asking if you considered at some point, at least at the beginning, to start with self-managed Kubernetes before adopting it, or you went straight like, let's manage the control plane and ourselves?
Yes. So one of the things, when we started managed Kubernetes, we're not as advanced as today, first thing. We still believe that even if we started today, we would need to go to manage our own control plane, because we have a lot of traffic, and we need to be able to debug up to the kernel level if something goes wrong. So it would be for us very, very difficult to use managed Kubernetes. Back then, it wasn't almost even a choice because it wasn't that advanced. But we actually believe that nowadays, there are very, very few use cases or very few companies that really require to use their own control plane. So our recommendation always is if you can use managed Kubernetes, particularly if you want to be on the public cloud. Obviously, if you're not, then it's another thing. But if you're in a public cloud, it's very unlikely that you need to run your own control plane, and it's always a good idea to go start with managed Kubernetes for sure. Okay,
and now let's dive a little bit into Kubernetes configurations that you described. So a lot of people were doing +1 here. They ask, like, for what use case you are using direct pod-to-pod communication instead of going application? I guess this is related to performance in terms of like connectivity.
Yeah, it's performance-based. So direct pod-to-pod communication needs to happen. So that's something that...
At your scale, I guess, yeah.
No, at any scale. So,
well, we could talk about that, but yeah, real scale.
No, what I mean is that this is something that how Kubernetes works. Like the traffic is always route pod-to-pod, even though you have an abstraction on top, which is service, the service layer. But service is really just an abstraction. It's not real in Kubernetes. Is what it does. So if you use, for example, Kubernetes services on the default way to implement Kubernetes services, which is through kubeproxy with IP tables, what it really does is only changes the IP tables NAT route of that every single node. But actually, the traffic is routed between pods. So And the reason why we do direct web routing is because of performance, but you have to have something. It's like...
They also ask about, you mentioned that you have 1,000+ nodes per cluster. Do you limit it somehow, or like in multi-clusters, or like, because apparently from 5,000 nodes, I've never been in such a setup, but at 5,000 nodes, I guess
we are not at
5,000.
Yeah, we are not at 5,000 nodes. No, we split it on several clouds. The reason why we have so many nodes is not because capacity, but because a little bit, and this is changing on newer clusters. So one of the things is that we migrate from cluster to cluster when we upgrade Kubernetes. So for example, we create a new cluster. If we change, for example, when we moved to Cilium, to put an example, we didn't move the cluster that was running. We created a new one with Cilium, etc. So because of how we started with Kubernetes, in which our developers were creating node groups for themselves, usually our instances were very small. So it's a little bit of an artifact of how you started. And because those instances were quite small and they were not shared, that ended up being a lot of nodes. I see that number being reduced as we move more to the nodeless mode that we have.
Okay, and someone is asking if you consider using IPv6 internally to, alleviate a little bit of the NAT and all those things in terms of networking.
So Cilium uses IPv6 by default.
Okay, then sorry about that. Okay. And I think this covers more or less, but if anyone in the audience wants to ask, because we're a bit running out of time, but there were lots of questions, so I guess if anyone... Oh, yeah, there's one here, yeah, in the corner. Aquí delante. O sea, el último asiento.
Sorry, what make you the decision to use Cilium rather than Istio, Calico, or any other network?
Two different questions. So in terms of Calico, so the reason why we didn't choose Calico is because Calico uses BGP, and it felt like if we were on bare metal, we probably would have used Calico, but because we're in a public cloud, using Calico felt like we were doing an extra abstraction layer that we didn't need with direct port routing. So the first thing is that we chose direct port routing. We were using at the beginning, for example, for AWS, a plugin that Lyft created, which is kind of the antecessor of what EKS is using nowadays. So that's why we rejected Calico from the beginning. And the reason why then we moved to Cilium is because once we had the decision of doing direct port routing, and we had to use several plugins, Cilium solved having just one plugin for multiple clouds.
What about Istio?
Istio.
Maybe some Istio maintainers here?
No, I forgot the question. So we tried Istio for a while when we were doing host-to-host encryption, and only for that. So we didn't want all the services abstraction on top. But yeah, we decided to give it a try to Service Mesh and Istio for host-to-host encryption. But because we didn't need and we didn't want all the extra abstraction on top, when then we discovered that Cilium was there and they were doing host-to-host encryption as well, we decided to just drop that POC of Istio. So yeah, I don't know. We gave it a try. We decided to do something else.
Thank you.
Okay, no more questions? Okay, yeah, thanks a lot for finally a real Kubernetes talk. Thank you.